So within a particular group here, so the mammalian globins, we're going to see about 30 to 50% identity between them. Same thing with invertebrate or plant globins. And then between different species, you're going to get like lower 10 to 20% perfect match. Okay. So percentage identity is looking at number of matches over number of pairs. So in this case, 7 over 14 would be 50%, or 4 out of 14 would be 29%. And as percent identity goes up, evolutionary time goes down. Okay? So the more similar they are, the more evolutionarily similar they are, okay, in terms of sequence. We can compare the sequences from related proteins to determine the probability or frequency with which certain amino acids would substitute with each other. Okay? So substitution is, oh, hey, here it was a leucine, now it's a valine, it's been substituted. Okay? And if you study a lot of sequences from a lot of different species, you can start to see patterns in what substitutes frequently. So substitution probability. A conservative substitution is the replacement of an amino acid residue in a protein by one that has similar chemical properties. Okay, so examples would be serine and threonine, or leucine and isoleucine, stuff that's kind of similar in size, similar in charge. We would call this conservative substitution. A non-conservative substitution is then kind of the opposite. We're talking about now we have different chemical properties or differences in size. So we're talking about taking something like arginine, which is very large and positively charged, and replacing it by maybe something like glycine. It's very neutral, it's very small. Okay? It's going to be very difficult for the glycine to fold up the way it needs to and behave in a similar way as the arginine. Okay? So it's kind of difficult to quantify this degree of similarity between the side groups. We can look at charge, we can look at size. Quantifying how close isoleucine and leucine are is really difficult, which is why we sort of use statistics across all these different sequences to get sort of a quantitative answer for us. All right, so if you align the sequences of proteins that we know are related, we assume the changes have already been filtered through the process of natural selection. Okay, so we're saying all the changes that were good stayed through time, all the changes that were bad got filtered out through time. Then we can assume that the frequency with which amino acids substitute for one another is a reflection of their true similarity. So stuff that frequently we see substituting, those things must be truly related. Okay? And so there's a couple different sort of ways to construct this, like compare a bunch of sequences and put together some sort of scoring or quantitative metric for how similar amino acid substitutions would be. One of them is BLOSUM, and it's also the only one we will talk about in this class. I think point-associated mutation or something, PAM is another one. Well, we won't discuss it here. Okay, so in our class, we're only going to talk about BLOSUM. This is block substitution matrix. That's what BLOSUM stands for. So it's a way to quantitatively measure similarity and differences between amino acids based on how frequently they substitute for one another. Substitution of one amino acid with another has similar properties is likely to have little effects on thermodynamics of protein folding. Okay, so again, that makes sense. Charge and size will kind of, if they're similar chemically, they're probably going to be able to fold the same way and then thus function the same way. This is the BLOSUM matrix from your textbook. I made an announcement. It's figure 511. It is the only one you should use when asked to do these problems. I will make this available after class. I know people in the back won't be able to see it. This was the reference sheet from the in-class exam last time, so I'll give it to you, even though when you're taking it online, you're free to use whatever you want. During the in-class portion, this is all you'll get, so familiarize yourself with it. It has the amino acids at the top, again, with their charge on them. We showed this figure. It has the alpha helix propensity scale. It has the hydrophobicity scale. It has the BLOSUM matrix down here for you, and it also has a bond energy and length table. So I'll release this right after class if it's not already up there in one of the resource folders. Okay. So when you go to read the matrix, first of all, it's only half of a matrix, but the other half, the flip side, would look exactly the same. Okay? So you don't. L substituting for K is the same as K substituting for L. It doesn't matter which way it goes. And so it's kind of confusing because what you'll read in the text or what you'll hear in some of these videos, it's saying imagine that the I-th amino acid is substituted by the J-th one. And so if you want to say, oh, tryptophan is replaced by phenylalanine, you would go for I, tryptophan is W. There's nothing to do here. So you'll need to go to phenylalanine and then go up to W. And that would be a score of 1 for that swap. And so, like I said, it's only half a table. Fine, there's only one set of each pair. So whenever you're looking for a substitution score for some pair, it doesn't matter which way you decide to go for it on the table. Okay? So these are scores that represent conservation. So an identical amino acid staying in the exact same place. And that's the diagonal here. Cytosine to cytosine, we have a 9. Tryptophan to tryptophan is a score of 11. An identical amino acid is always going to have a higher score than any substitution with a different amino acid. It would always be best to keep it perfectly, identically conserved than to swap it with anything. And then conservative substitutions are going to be better than non-conservative substitutions, okay? And so again, these are positive numbers. High scores represent conservative substitution. Negative scores represent non-conservative, something that doesn't want to happen. Yes? Why do you think that is? So like, for example, we have like C to C is a score of 9, or tryptophan to tryptophan is a score of 11, whereas some of the other ones on the diagonal, like alanine, is only a 4. So that was the question, is why are they different when it's that perfectly identical substitution? So what do you think? Okay. Sort of, yeah. Yeah. So what can cysteine do? It can make disulfide bonds. Tryptophan is huge. Like, it's just one of those things where keeping, like, actually changing any of those things that participate in something unique would be a much more difficult to accomplish energetically. And so through time, that swap just really isn't going to happen. The ones that are a lower score are stuff like alanine. It's small. It's neutral. So while it's great to keep alanine, leave it alone and conserve it, it's not as quite it's not conserved as often evolutionarily than something like cytosine, which participates in disulfide bonds. And those disulfide bonds are very important, for example, in ribonuclease A, to the successful like enzymatic activity of it. Does that make sense? Yeah. So the big stuff, the stuff that's charged or important, yes. So what 0 represents, this is a great question. What 0 represents is random chance, okay? A positive score represents that it is greater than a random likelihood that these two would swap. That is a swap that actually happens evolutionarily through time. Or if it's conserved, it's not a swap at all. That also happens. A negative score means it is less likely to happen. And a score of 0 means that it is the same likelihood of those two swapping as just happening randomly. Okay? It's a really good question.